The most amazing field of modern inorganic chemistry is coordination chemistry. Coordination chemistry helps to understand the complexity of compounds. So we are now starting with a new chapter, that is coordination compounds. What are coordination compounds? A coordination compound consists of a central metal atom or ion surrounded by atoms or molecules. Here we are considering the example of a chemotherapy drug, that is cisplatin, which has the formula of PT NH3 Cl2. So this is a coordination compound in which the central metal ion is platinum, and platinum is surrounded by the atoms or molecules of NH3, that is ammonia, and chloride ions. The species which surround a central metal atom or ion are called as ligands. So in this case, ammonia and chloride ions are ligands. These ligands, they are directly connected to the central metal ion with the help of a coordinate bond. How is this coordinate bond formed? Coordinate bond is formed when there is sharing of electrons taking place between that of the central metal ion and that of the ligand. A coordinate bond is represented by an arrow. The arrow head, it points towards the electron acceptor. The central metal atom or ion which is present, they are usually electron deficient species, means they do not have enough electrons to complete their octet. Hence they accept electrons from the ligands, and the ligands act as electron donors. Usually coordination compounds having central metal ions are very common. So here in cisplatin, the central metal ion is platinum, and ammonia and the two chloride ions, they are ligands. So here nitrogen and chlorine, that are ligands, they are electron donor, while platinum is electron deficient, accepting electrons from the ligand and hence forming a coordinate bond. We have already studied ionic equilibria. In that we have studied what are Lewis acids and Lewis bases, right? So this coordination compounds, they also can be looked upon as Lewis acid base interactions. So the ligands which are acting as electron donors are Lewis bases, and the central metal ion which accepts the electron from the ligands will act as Lewis acids. Let us now study the types of ligands. There are three types of ligands, namely monodentate ligands, polydentate ligands, and ambidentate ligands. First are the monodentate ligands. Monodentate ligands are one wherein a single donor atom shares an electron pair to form a coordinate bond with the central metal ion. For example, ligands like Cl, chlorine, OH group, that is hydroxide group, CN, that is cyanide group, etc. So in these cases, if we look at chlorine, oxygen and nitrogen, then there is only one donor electron pair which is present, and hence it is considered as a monodentate ligand. From the name itself, monodentate, mono means one, and hence monodentate ligands are those wherein there is only one donor atom present. Next are the polydentate ligands. The term poly means many, hence a polydentate ligand has two or more donor atoms which are linked to the central metal ion. Let us consider the example of ethylene diamine and oxalate ions. Since there are two ligands present in both the examples, they are called as bidentate ligands. Here is the structure of ethylene diamine. In this structure, it is evident that ethylene diamine has 2 points of attachment with the metal ion, where each nitrogen atom donates a pair of electrons. Since there are two nitrogen donor atoms present, it is called as a bidentate ligand. The second example is of the oxalate ions. In oxalate ions, there are 4 oxygen atoms, so we cannot conclude that all these 4 oxygen atoms are going to donate its electron pair to the central metal ion. You can see that in the 2 oxygen atoms which are present below, their capacity is full, while those which are there on the top, they have the capacity to donate their electrons, right? So hence it is a bidentate ligand because only the two oxygen atoms which are present at the top will be able to form a coordinate bond by donating their electrons to the central metal ion. The two oxygen atoms which are present below, they have already formed two coordinate bonds and hence their capacity is full. While the oxygen atoms which are above, they have formed only one coordinate bond and hence they can still denote a pair of electron to form another two coordinate bonds, and that is why it is classified as a bidentate ligand. Next is the example of ethylene diamine tetraacetate ions, which is also called as EDTA. This is the structure of EDTA. In this, the central metal ion, it is bonded to two nitrogen atoms and four oxygen atoms. Hence, it is a hexadentate ligand. The other four oxygen atoms here, they are not considered as ligands because their capacity is already full because they have formed two coordinate bonds. A simple way to identify the ligands are the species with the negative charge. For example, oxygen, nitrogen, chlorine, etc. Carbon has a positive charge. Hydrogen has a positive charge. So they are not considered as ligands. So basically under polydentate ligands we can have bidentate ligands, tridentate ligands, tetradentate ligands and hexadentate ligands. If it is bidentate, then there will be two ligands present. If it is tridentate, there will be three ligands present. If tetradentate, four ligands will be present, and if it is hexadentate, there will be six ligands present. Next are the ambidentate ligands. Ambidentate ligands are those wherein the ligands have two donor atoms but uses the electron pair of only one ligand to form the coordinate bond with the central metal ion. Let us take the example of NO2 group. So here it has two donor atoms, that is nitrogen as well as oxygen, but out of the two only one donor atom is going to link to the metal. So let us take the metal as M. So either it is going to form coordinate bond MONO, or the other way is M with nitrogen, that is MNO2. Similarly for SCN, it has two donor atoms, that is sulfur S and nitrogen, but only one can be linked to the metal. Let us consider M as the metal. So metal will form a coordinate bond with either SCN or M with NCS. Let us now study some terms which are used in coordination chemistry. First is the coordination sphere. The central metal ion and the ligands which are linked to it, they are enclosed in a square bracket, and this is called as the coordination sphere. When the coordination sphere comprises of a central metal ion along with the ligands attached to it and they carry a net charge, then it is called as a complex ion. Sometimes there are ionizable groups which are present outside the brackets. They are called as the counter ions. For example, the compound K4FeCN6. In this, the K4 ions, they are outside the bracket and hence they are counter ions. The ionization of the compound takes place as follows. The next term is the charge, number of complex ion and the oxidation state of the metal ion. The net charge which is present on the complex ion is called the charge number. It is the algebraic sum of the charge which is present on the metal ion and the ligands. However, the charge which is carried out by the central metal ion is the oxidation state. It is also represented as OS. Let us consider the example of the complex FeCN6. You have the coordination bracket raised to 4 minus. So the 4 minus which is present here is the charge number of this particular complex. Let us now calculate the oxidation state of the central metal ion, which is the ion Fe. So the formula to calculate the oxidation state of the central metal ion is oxidation of the central metal ion plus the charge which is present on the ligand is equal to the net charge on the complex. So since we are calculating the oxidation state of Fe, we will write it in this way, plus there are 6 ligands, so 6, and the charge which is present on Cn, that is -1. So it will be 6 into -1 is equal to net charges -4. So the next step will be oxidation state of Fe -6 is equal to -4. Now we have to simplify this further. So oxidation state of Fe is equal to -4 plus 6. Hence we get the oxidation state as +2 for iron. This is how you calculate the oxidation state for the central metal ion. If there is no net charge given, then you will take it as equal to 0. The next term is the coordination number of the central metal ion. It is also represented by capital letter Cn. Here, let us consider the example of the complex CONH3 4 times Cl2 and a net charge of +1. There are 4 ammonia molecules and 2 chloride ions. So in total there are 6 ligands which are attached to the central metal ion cobalt. So basically there are 6 donor atoms which are attached to the central metal ion. So the coordination number of the metal ion attached to the monodentate ligand is equal to the number of ligands bound to it. In simple way, I would say coordination number is the number of ligands which are attached to the central metal ion. So here in this example, the coordination number is going to be 6 since we have 6 ligands, 4 ammonia molecules and 2 chloride ions. If we take the example of ethylene diamine, then there are 2 donor atoms and hence the number of ligands are 2 and it is a bidentate ligand. So the coordination number is 2. So how would you define coordination number? Coordination number of a metal ion is the number of ligand donor atoms directly attached to it or the number of electron pairs involved in the coordinate bond. The next term used in coordination compounds is double salts and coordination complexes. When 2 or more stable compounds combine in a stoichiometric ratio, then it gives rise to substance, namely double salts and coordination complexes. Let us first study what are double salts. A double salt dissociates in water completely into simple ions. Let us take the example of Mohs salt. It has a formula of FeSO4 NH4 twice SO4 dot 6H2O. So Mohs salt in the presence of water will dissociate as Fe2 plus. Since we are having 2 times SO4, so it will be dissociated as 2 times SO4 2 minus and 2 molecules of NH4 plus. Let us take another example of carnallite with the formula KCl MgCl2 6H2O. When this carnallite along with water dissociates as K plus plus Mg2 plus 3 times Cl minus. Next are the coordination complex. A coordination complex dissociates in water with one complex ion. So let us take the example of K4. In the coordination sphere you have FeCN 6 times. So when it comes in contact with water, it is going to dissociate as 4 times K plus ions plus FeCN6. So here potassium is the counter ion since it is present outside the coordination sphere and FeCN6 is the complex ion. So coordination complexes when comes in contact with water dissociate giving the counter ion and the complex ion. The complex ions, they are present inside the bracket, the square bracket, which is called as the coordination sphere. Next is the Werners theory of coordination complexes. The first attempt to explain the type of bonding in the coordination compound was made by Werner. Now there are about 4 postulates that we need to study under the Werners theory of coordination complexes. The first postulate is, unlike metal salts, the metal in a complex possesses 2 types of valencies. So the first is called as the primary valency, which is ionizable, and the secondary valency is non-ionizable. So basically, the primary valency is the oxidation state of the metal ion, and the secondary valency, it is the coordination number of the metal ion. The second postulate is the ionizable sphere consists of entities which satisfy the primary valency of the metal. The primary valencies are generally satisfied by anions. This means that the metal ion will exercise towards the negative group so that its normal charge is satisfied by the formation of simple salts. For example, the primary valencies of platinum, cobalt, copper and silver are 4, 3, 2 and 1 respectively. So they will produce simple salts like PtCl4, CoCl3, CuCl2 and AgCl respectively. The third postulate is the secondary coordination sphere. It consists of entities which satisfy the secondary valencies and are non-ionizable. So the entities which are present in the secondary coordination sphere, they are not going to ionize, that is, they are not going to break up into simple species. The secondary valencies for a metal ion, they are fixed and satisfied by either anions or neutral ligands. The number of secondary valencies is equal to the coordination number. An example of this would be cobalt 3 plus ion. It has a secondary valency of 6. Hence, CO3 plus will form complexes like CONH3 6 times the whole raised to 3 plus, CONH3 5 times Cl coordination sphere the whole raised to 2 plus, CONH3 4 times Cl2 the whole raised to plus 1, etc. And the last postulate is the secondary valencies, they have a fixed spatial arrangement around the metal ion. The two spheres of attraction in the complex CONH3 6 times coordination sphere Cl3 are shown as follows. So here the species which are present inside the coordination sphere are CONH3 6, whereas Cl3 is acting as a counter ion which is present outside the coordination sphere. Cobalt is the central metal ion. Then you have the ligands, ammonia molecules which are 6 times which are present inside this coordination sphere, and this coordination sphere is also called as the secondary valency, whereas Cl3 which is present outside, the bracket which is used for denoting the Cl3 present outside is called as the ionization sphere or the primary sphere. Because of coordination compounds having a fixed spatial arrangement, if there are 6 ligands, then it will have an octahedral structure. If 4 ligands are attached to the central metal ion, or if the coordination number is 4, then the coordination complex will have a square planar or a tetrahedral structure. Next topic is regarding the classification of complexes. First are the homoleptic complexes. Let us consider the example of the coordination compound CONH3 6 coordination sphere the whole raised to 3 plus. In this coordination complex, there is only one type of ligand, that is ammonia molecule, that is attached to the central metal ion. Hence, the complex in which the metal ion is bound to only one type of ligand are called as homoleptic complexes. From the term homo, it is very much evident that homo means one or same. Next are the heteroleptic complexes. The term hetero means many or different. Let us consider the example of the complex CONH3 4 times, chloride ions twice, coordination sphere the whole raised to plus. So you can see there are two types of ligands here which are attached to the central metal ion, that is NH3 and chloride ions. Hence, complexes in which metal ions are surrounded by more than one type of ligands are called as heteroleptic complexes. Next is the classification of complexes based on the charge which is present on the complex. First are the cationic complexes. If the complex has a positively charged coordination sphere, then it is called as a cationic complex. For example, ZnNH3 coordination sphere the whole raised to 2 plus is an example of cationic complex. Next are the anionic complex. When the coordination compounds have a negatively charged coordination sphere, then they are called as anionic complexes. For example, NiCN4 the whole raised to 2 minus. Next is the neutral sphere complexes. A neutral complex does not possess cationic or anionic coordination sphere. Example of neutral sphere complex is NiCO4 the whole raised to 0. So here there is neither a plus charge or a minus charge, hence it is a neutral sphere complex. Some points for you to remember the Werners theory of coordination complexes. The central metal ion, it shows two types of valencies, that is primary and secondary valency. Also keep in mind the metal atom or ion, it works towards satisfying its both valencies, that is primary as well as secondary valency. Next topic is the IUPAC nomenclature of coordination compounds. There are certain rules that we need to follow which are recommended by the IUPAC for naming the coordination compounds. The first rule is, in naming the complex ion or neutral molecule, we are supposed to name the ligand first and then the metal. So here we are having a neutral complex, that is NiCO4. So in case of this, first we need to write the name of the ligand. So the ligand here is carbonyl. But how many times? 4 times. So tetracarbonyl, and the name of the metal ion, that is nickel. And in the brackets we are going to write 0 since it is a neutral complex. The second rule is, the names of anionic ligands are obtained by changing the ending "ide" to O and "ate" to "ato. These two tables help us to understand the changes that we need to bring in case of anionic ligands. So first is bromide. So as I told you, "ide" is changed to O. So bromide becomes bromo. Similar in case of chloride, fluoride, iodide and cyanide. The other conversion is the ionic ligands ending with "ate" to "ato. So if you look here at sulfate, it is ending with "ate." Hence the conversion becomes sulfato. Similar in case of nitro, it becomes nitrato. So now if it is an anionic complex, then how do you write the name of the central metal ion? If it is aluminium, then it becomes aluminate. If it is cobalt, it becomes cobaltate. So keep in mind, while writing the name of the anionic complex, the central metal ion is written with suffix ending with "ate." So when you write the name of an anionic complex, first you will write the number of ligands present, then the name of the ligands ending with depending if it is "ide" or "ate, and finally the name of the central metal ion with suffix "ate." Let us understand this rule by solving an example. So if I give you the example of ferrocyanide ion with the formula FeCN6, coordination sphere the whole raised to 4 minus. Now this is an anionic complex because the coordination sphere is raised to a negatively charged species, right? So how are you going to write the name? First we need to see the number of ligands. So there are 6 ligands. So hexa, and then the name of the ligand is Cn. Cn means cyanide. So ide is converted to O. So you will write it as cyno. So hexa, cyno, and then the name of the central metal ion. So this is Fe, which means ferrous, right? So because it is anion, we have to put 8. So it will be ferrate. So hexacyanoferrate, and then you need to find the oxidation state. So how are you going to find the oxidation state of Fe? So oxidation state of Fe plus 6 times the number of ligands, so that is Cn corresponds to a value of -1, which is equal to -4. So oxidation state of iron -6 is equal to -4. The next step will be oxidation state of iron is equal to -4 plus 6. After calculation you get the answer as +2. So in the brackets you will write it as 2. So the oxidation state of the central metal ion Fe is 2 for this particular anionic complex. The next rule is the name of a complex is one single word. So there must not be any space between different ligands names as well as between ligand name and the name of the metal. So just now you saw when we were solving for anionic complex, I did not put any comma or I did not leave any space between the name. The fourth rule is after the name of the metal, write its oxidation state in Roman number which appears in parenthesis without any space between the metal name and parenthesis. So you can check this example here. There is no space between the metal name and the brackets, which are called as parenthesis. The fifth rule is if complex has more than one ligand of the same type, then the number is indicated with the prefixes di, tri, tetra, penta, hexa and so on. Let us solve an example to understand this rule. Pt NH3 4 times Cl2 the whole raised to 2 plus. So here we need to check the number of ligands. So there are 4 ligands of ammonia and 2 of chlorine. Hence you are going to write it as NH3 is written as amine. So we have 4 amine ligands. So it will be written as tetra amine 2 times chloride ions. So hence di, chlorine or chloride ions are written as chloro. So hence it will be written as dichloro platinum and then the oxidation state which is 4. I have already told you how to calculate the oxidation state of the central metal ion. Why did I write the name of the ligand amine first and chloro second? Because we have to follow the alphabetical order. The next rule explains the same, that is, for the complex having more than one type of ligands, they are written in alphabetical order. Suppose 2 ligands with prefixes tetra-aquo and dichloro, then while naming in alphabetical order, we have to write tetra-aquo first and then dichloro. We are not going to take the number of ligands first, the name of the ligand is considered, that is aquo and chloro. We are not going to consider tetra and di, we are going to consider the name of the ligand, that is aquo and chloro. The next rule is if the name of the ligand itself contains numerical prefix, then display number by prefix with bis for 2, tris for 3 and tetrakis for 4 and so on, and put the ligand name in parenthesis. So here are some examples given, that is ethylene diamine 3 times. So instead of writing ethylene diamine, you can also write it as En3 and it would appear as tris ethylene diamine or tris ethane 1,2 diamine. So this is a chelate ligand which is having complex name. Let us understand this with one more example, that is COEN twice Cl2, the coordination sphere and Cl is out. So in this case first we need to identify the ligands. So there are 2 types of ligands, that is En, that is ethylene diamine, and the chloride ions. So it should go according to the alphabetical order. So first, since there are 2 chloride ions, we will write it as dichloro bis ethylene diamine cobalt, then the oxidation state of cobalt which is found to be 3, and then chloride. Now why am I writing this as chloride? Because it is outside the coordination sphere. It is acting as a counter ion here. The last rule is the metal in cationic or neutral complex is specified by its usual name, while in the anionic complex the name of the metal ends with 8. So if it is a neutral or a cationic complex, that is if it is having a plus charge or it is raised to 0, then we are going to write the name of the central metal ion as usual. However, in case of an anionic complex, we write the name of the central metal ion with the suffix ate. Let us now solve some examples based on the rules we have studied. First, let us take the examples of anionic complex. Anionic complexes are those wherein the coordination sphere is negatively charged. So as you can see in all the three examples here, it is raised to 2 minus, 3 minus and 4 minus, and hence they are example of anionic complexes. So what is the rule for writing the anionic complexes? First you are going to write the number of the ligands, then you are going to write the name of the ligands depending on the conversions, and then the name of the central metal ion ending with the suffix ate, and then the oxidation state of the central metal ion. So let us take the first example, that is NiCN4 the whole raised to 2 minus. So first we need to see the number of ligands. So cyanide, that is Cn, is the ligand and it is 4 times. So it will be tetra. Since cyanide is ending with ide, we need to write it as cyano. So it will be tetra cyano, and since it is anionic, nickel will become nickelate. So tetracyanonickelate. Then we need to find the oxidation state of nickel, which will come as 2. So it is tetracyanonickelate 2 ion. We need to put that 2 in parenthesis. When you write the IUPAC name, care should be taken that the first letter should be capital and then there should be no space or comma in between the name. Let's solve the second example, that is CO C2O4 thrice the whole raised to 3 minus. The name of the ligand C2O4 is oxalate, so it will be written as oxalato. So how many times is the ligand? 3 times. So it will be trioxalato. The central metal ion is cobalt. Since it is anionic complex, it will become cobaltate. And then 3, which is the oxidation state. So the name becomes trioxalato cobaltate 3 ion. Now don't make a mistake, that is the net charge which is present is not the oxidation state of the central metal ion. You have to calculate the oxidation state of the central metal ion using the formula that I have taught you. The next example is FeCN6 the whole raised to 4 minus. This also is an anionic complex. So again here we have the cyanide group, so cyanide will be written as cyano. How many ligands? 6. So 6 is written as hexa cyano. Fe is ferrous, but since it is an anionic complex, we have to write 8 suffix. So it will become hexa cyano ferrate. Then you need to find the oxidation state of ion here, which will come as 2. So the IUPAC name will become hexacyanoferrate 2 ion. Always keep in mind the oxidation state of the central metal ion is written in Roman numbers. The next set is compounds containing complex anions and metal cations. The first example here is Na3. Inside the coordination sphere we have CONO2 6 times. We know that any species which is outside the coordination sphere act as a counter ion. So you will write the name of it as usual, that is sodium. Then the number of ligands is 6, so it will be hexa. The ligand is nitrite, so we will write it as nitro. So sodium hexa nitro, and since anion is present here, cobalt will be written as cobaltate, and then we need to write the oxidation state of cobalt, which comes as 3. So the IUPAC name is sodium hexanitrocobaltate 3. Let's move on to the second example. Here we have K3 outside the coordination sphere, so we are not going to write that as tri-potassium or something like that. It is a counter ion, so even after ionization it will be 3 times K plus, so we are going to just mention it as potassium. So potassium tri, we have the ligand as oxalate, so it will be written as oxalato. So potassium trioxalato. Because an ion is present, aluminium will be written with the suffix ate, so it will be written as aluminate. So potassium trioxalato, aluminate, and then the oxidation state of aluminium, which comes as 3. The next example is Na3, which is acting as a counter ion, and inside the coordination sphere we have AlF6. So sodium we are going to write as it is. So sodium, the central metal ion is aluminium here and the ligand is fluoride. How many times? 6 times. So sodium hexa fluoroaluminate, and then the oxidation state of aluminium, which comes as equal to 3. Next are the cationic complexes. Cationic complexes are those where the coordination sphere has a positive charge. Keep in mind, when it is a cationic complex, the name of the central metal ion is written as usual. You need not put any suffix there. So let us start with the first one, which is CuNH3 4 times the whole raised to 2 plus. So we have 4 ligands of ammonia, and ammonia is written as amine. So tetra amine copper, then you need to find the oxidation state of copper, which comes as 2. So the name is tetraamine copper 2 ion. The next example is FeH2O 5 times NCS the whole raised to 2 plus. In this example we have 2 types of ligands. One is H2O and the other one is NCS. Water is aqua and NCS is isothiocyaneto. So now we need to arrange the ligands in alphabetical order. So of course aqua will be written first and then isothiocyaneto. So we have 5 ligands of aqua. So penta aqua, isothiocyaneto, Fe is iron. Then we need to find the oxidation state of iron, which comes as 3. So the IUPAC name is penta aqua isothiocyaneto ion 3 ion. Keep in mind, for cations we write the name of the central metal ion as usual. We need not change it by putting suffix ate. That is only for anionic complex. Next is a chelate ligand, which is a complex type of ligands. So inside the coordination sphere we have PTEN twice, SCN twice the whole raised to 2 plus. So I have already mentioned in the rule, if it is a chelate type of ligand, then we are supposed to use the prefix bis, tris, tetra, kis, etc. Here En stands for ethylene diamine and SCN is thiocyaneto. So again we need to follow the alphabetical order, and according to that ethylene diamine will be written first. Here ethylene diamine is twice, so we will write it as bis ethylene diamine dithiocyaneto platinum, and then the oxidation state of platinum, which is 4. So the IUPAC name is bis ethylene diamine dithiocyaneto platinum 4. You can put ethylene diamine in the bracket since you are writing it in full form, which you are supposed to do. The next set consists of compounds containing complex cations and anions. In the previous set we studied complex anions and metal cations. Now it is the opposite of it. So the first example is, inside the coordination sphere we have platinum Br2 NH3 4 times, and outside the coordination sphere we have Br2. Here we have 2 types of ligands, that is amine and bromo. So according to alphabetical order, amine will go first. So 4 times amine, so tetraamine dibromo platinum, then the oxidation state of platinum is found to be 4, and the bromide which is present outside the coordination sphere is written as it is, that is bromide. The second example is inside the coordination sphere we have CONH3 5 times CO3, and outside the coordination sphere we have a chloride ion present. So here we are going to write as pentaamine, CO3 is carbonato, cobalt, oxidation state of cobalt is 3, and chloride. The next example is inside the coordination sphere we have COH2O NH3 5 times, and outside the coordination sphere it is I3. So now again we have two types of ligands, that is aqua and amine. Now you will get little confused since both the ligands are starting with the same alphabet, that is A. So now look at the second alphabet. For amine it is M and for aqua it is Q. So in this case we will write amine first. So penta, amine, aqua, cobalt, then the oxidation state, that is 3, iodide. The last set is of neutral complexes. Neutral complexes are those which do not include a plus or a minus charge on the coordination sphere. The first example is CONO2 thrice NH3 thrice. Here we have two types of ligands, that is amine and nitro. So of course according to alphabetical order we will write amine first. So it will be triamine, trinitro, cobalt, then the oxidation state of cobalt, which is 3. The next example is FeCO5. So it will be penta, CO is the carbonyl group. So pentacarbonyl ion, if you find out the oxidation state of ion, it comes as equal to 0. So the IUPAC name is pentacarbonyl ion in the bracket 0. The last example is RHNH3 thrice SCN thrice. Here there are two ligands, that is amine and thiocyanato. So according to the alphabetical order you will have to write amine first. So triamine, trithiocyanato, and RH stands for rhodium, and the oxidation state of rhodium is found to be 3. So I hope you are now clear in how to determine the IUPAC names of coordination complexes.